So, you see, if F friction is equal to the effective force, is equal to the effective force pulling the body, then what do you think will happen? If friction F is equal to T cos theta, what do you think would happen? Yes, let me take your views. If friction is equal to T cos theta, what do you think will happen? Yes, Inshira, Edita, Gloria, Oh, no idea.
There'll be static equilibrium.
There will be static equilibrium or dynamic equilibrium. Okay, well, here, Gloria, I'll accept dynamic equilibrium because the body is pulled to be moving, right? What she means is that if F is equal to T cos theta, then the net force acting along the horizontal is equal to 0. And if the net force acting along the horizontal is 0, two things. Either the body is stationary, static equilibrium, or the body is moving at a constant velocity, dynamic equilibrium. Okay? In that case, if the net force acting horizontally is 0, would there be an acceleration? Would there be an acceleration?
No.
Okay, so if F is equal to this, acceleration is equal to 0. Acceleration A will be equal to 0 because the net force acting on it is 0. Now, if we have a situation where there is a difference between T cos theta and F, then the net force acting horizontal is not 0, and so the body would accelerate. So let's see. Let's calculate. Let's see if T cos theta would be greater than F. T is 1,300 cos of 35. And this is equal to, please compute this for me. 1,300 times cos of 35. Quick one. Please, when you are computing, you have to be sure if your calculator's angular measurement is on degree. D. The moment it's on radian, R, it affects your value. So what did you get?
1,064.
1,064. Exactly.
0.897.
Okay, so point and 1,064.9 Newton. Okay, now let's compare T cos theta and F. We realize that T cos theta is far greater than F. Okay, and once there is difference, then it means there is a net force. So the net force or the resultant force between this T cos theta and the friction is equal to 1,064.9 minus 100. And in Newton's second law of motion, whenever there is a net force or resultant force, a body accelerates. Please listen to the second law. Okay, the first law is saying, please mute yourself if you haven't muted. I'm getting a very bad feedback. The first law is saying that a body at rest will continue to be at rest A body in motion will continue to be in motion at a constant velocity unless an external force or net force or a resultant force acts on the body. It means that whenever there is a net force, resultant force, or an external force, the body would accelerate. Okay, so because there is a net force, the body would accelerate, and this will give us, let's calculate the net force, subtract 100 from 1064.
It's 964.9.
964.9. All right. So this is the resultant force acting on the body. And as we just understood, whenever there is a resultant force, the body accelerates. So let's find the acceleration of the body. Newton's second law is saying that every force is measured by its mass times the acceleration. So m times a is equal to 964.9. We were given the mass of the body. So the acceleration becomes 964.9 divided by the mass, which is 210. So calculate the acceleration of the body for me.
4.6
A 4.6 meter per second
second
squared.
square.
I'll beat you when you get the unit wrong. Good. So this is the acceleration of the body, and we are asked to find the distance. So using one of the equations of motion, either v squared is equal to u squared plus 2ax, we can easily calculate for the acceleration of the body. We can also use s is equal to ut plus half at squared. But here, we'll need equation 1 to determine the time. So please use this to calculate for the acceleration, the distance covered by the body for me. Start with. I'm waiting for your answer. Use the equation in the bracket to find the distance covered.
Mr. Adria, please, I can't see the down part.
I hope you can see.
Yes, please.
So 100 divided by 9.2. 11 point. Gloria, 11 point.
Mr. Adria, please, I'll come.
Laurentia, 11 point. Come again. Okay, so 10.87. It's 10.87 meter. So this is the distance covered. Please, are we fine?
Yes, please.
Yes, please.
We can, as I said, we can also use this equation, the other equation of motion. But before we can use this, we have to know the time. So using equation 1, we can find the time. And here, t would be equal to b over a, because u is 0. And what is v? V is 10. A is where is A? 4.6. So 2 point what? 10 divided
17.
2, so 2.17 seconds. So when you substitute it into this, you get the distance covered. So do it. Substitute the time. U is 0, so straight away this side goes to 0. U is 0, so this side goes to 0. You have A, we have T, and use that to determine the time. I'm waiting for you. As I use that to calculate for the distance, sorry. And you should get the same value, 10.87. Are we there?
Yes, please.
Rafin, are you there?
Yes, please.
Okay. All right. So that's it. That's how to go about question 2D. Question 3, let's jump to C. 3A, define. We won't define. B, state the law of conservation of linear momentum. We will state. BII, state and explain true practical application of the law of conservation of linear momentum. We've said that. Recoil of a gun, the launching of rockets, or the proportion of the jet engine, and so on and so forth. Then C. Let's see. Can I clean the board? Can I clean the board? Can I clean the board?
Please, you can clean the board.
Okay. Two particles of masses m1, m2. Oh, okay. Okay, two particles of masses m1, m2, and initial velocities u1, u2, and final velocity v1, v2, respectively after collision, show that the momentum is conserved after their momentum is conserved after collision. Okay. So a 2-in-1 situation. Either, so if two masses collide, either use equation 3 or equation 2 to prove this. Let's consider masses m1 and then m2. Now, when m1 and m2 collide, m1 exerts a force F1 on m2, then m2 also exerts a force F2 forces same magnitude, opposite in direction. Okay, so if we take Newton's third law, by third law, F1, magnitude of F1 is equal to magnitude of F2, but their directions are opposite. This is the third law. Action and reaction are equal, but opposite. If we take F1, force F1 can be determined by its mass m1 times its acceleration. And the acceleration of m1 is equal to its final velocity given as v1 minus its initial velocity u1 divided by the time taken for the exertion of the force on the masses. Therefore, F1 becomes m1 v1 minus u1 on t. Are we there? Are we there?
Yes, please.
Now, considering F2, F2 would also exert equal magnitude of force on the mass 1. So F2 would be equal to m2 times the acceleration of 2. This will also be m2 times v2, the final velocity, minus initial velocity, divided by t. Now, when two bodies collide, when two bodies, particles or masses collide, okay, these two dusters, the time taken for collision of this, exertion of the force on this, and the time taken for this on exertion of force on it, the same. So T is equal for both masses. That's why T remains as it is in the second situation. Now let's put the expression for F1 and F2 respectively into this third law equation. So we have M1 V1 minus U1 on T is equal to, don't forget there is a minus here, minus M2 V2 minus U2 also on T. Laurie, are you there?
Yes, please.
Since the time for exertion of the force on each are the same, T would cancel out. Okay, so we have M1 V1 minus M2 U2 is equal to minus M2 V2 plus M2 U2. Now let's group all the like terms. Okay, UU at one side, VV at one side. And since this is negative, we are bringing it to its positive counterpart. So we have M1 V1 plus M2 V2. Then we are also sending this to its positive counterpart. So M2 is equal to M2 U2, okay, plus hold on, let me see. Oh, this must be M1 M1 U1. Okay, this must be M1. So plus M1 U1. Now look at what we've done. This is sum of momentum of the two bodies after. So this is after momentum after collision. And then this is momentum before. And the law of conservation of linear momentum says that for any two interacting bodies, the sum of momentum before is equal to the sum of momentum after collision. And we've proven that using Newton's third law of motion. Please, is that okay? Is that okay?
Yes, please.
We can also use Newton's second law. Here we use the third law. What does the second law, Newton's second law of motion says? It is saying that in the absence of external force or in an isolated system, the rate of change of momentum is always conserved. So F is equal to dp on dt. dp is the change in momentum, dt is the change in time. So when we consider two masses, m1, m2, the sum of the rate of change of their momentum must always be conserved, okay, when there is a force F acting on the body. So it means that if we take the P1, the rate of change of momentum of 1, mass 1 with respect to time, plus the P2 with respect to time. And this can only happen when there is an external force. What is dp? Change in momentum is mass times velocity, initial velocity minus final velocity minus initial velocity, all divided by t. Sorry, no. This is dp. So mv minus mu. This is change in momentum dp or delta p. So let's find the change in momentum of the first mass, add it to the change in momentum of the second mass. Then when there is no external force, we will see what will happen. So the P1 dt would be equal to mv P1v minus m1 u1 all on t. And this is equal to m1 v1 minus u1 all divided by t. This will be it for the P1 dt. Please, are we fine? We are looking for this, they're looking for this, then we add. So we've done it for this one. Okay, which is this? We are going to do it for the P2 on changing time. Are we clear? So the P2 on the T, change in momentum of 2 with time will also be M2 V2 minus U2 divided by the T. Or let me use, okay, I use T, so divided by T. And T is maintained in each situation because, as I explained earlier, it takes equal time for their interaction or collision. So M2 V2, okay, minus M2 U2 all on T. Let's add it is this plus this. So let's add this, what we have here and then what we have here. F is equal to M1 V1 minus M1 U1 all on T plus M2 V2 minus M2 U2 all on T. Now, since time is equal, it's equal to both masses during collision. F, we can we can multiply through by T to multiply what we have here. So we have M1 V1 minus M2 M1 U1 plus M2 V2 minus M2 U2. Now, in a situation where this collision occurs in isolated system, when there is no net force, it means that when there is no net force acting on a system of colliding bodies, F is equal to 0. So if F is equal to 0, then we can easily conclude that momentum will be conserved, in the sense that here, let's straight away group all the positives at one side and all the negatives at one side. Okay. So every negative, this one and this one will be sent to the other side. So M1 U1 plus M2 U2 is equal to M1 V1 and then plus M2 V2. M1 V1 plus M2 V2. Also confirming that momentum, sum of momentum before collision is equal to the sum of momentum after collision, confirming the law of conservation of linear momentum. So all that I'm trying to say is that you can use either Newton's second law of motion or third law of motion to prove the law of conservation of linear momentum. Class, are we fine?
Yes, please.
Yes, please.
So the choice, I'm sure you have identified where perhaps if you got it correct, you can see. If you got it wrong too, you can easily see from what we've been doing. Lauricia, are you fine? Okay. Then D. The D question is saying that two particles, okay, in the diagram below, a body A traveling with a velocity UA collides perfectly elastically with another body B initially at rest. This is actually WASI 2021 physics question, which was modified a little bit. In fact, we picked the question up and then modified it a little bit for you to try. So if you have solved that WASI question before, I think it will give you the tip, the tip off in answering this. So we have two masses, A and B. Mass A moving with an initial velocity UA. Okay. Then colliding with a stationary body B. Okay. Now we are told that the two collide perfectly and is elastically. So the collision, the nature of collision between them is perfectly elastic collision. And editor, in perfectly elastic collision, what happens? In perfectly elastic collision, what happens? Yes, editor. Hey, editor is not here. Oh, editor, you are here. Irene,
Stage, yeah.
in perfectly elastic collision, what happens? Or
Please,
what can you say? Mhm.
please, both momentum and kinetic energy of the bodies are conserved.
Absolutely. So there is a conservation of both momentum and kinetic energy. So once there is a conservation for this, write an equation for conservation of momentum, write an equation for conservation of kinetic energy. So MA UA plus MB UB must be equal to this must be equal to MA VA plus MA, sorry, MB VB. Now, fortunately for us, we are told the initial velocity of B is 0 because B initially was stationary. So this part go to 0. So MA UA is equal to MA VA plus MB VB. 2. We are also told that calculate the initial velocity of A if after, okay, we are earlier told that the mass of A is twice the mass of B. Mass of A is twice the mass of B. So MA is equal to 2 times MB. So if MA is equal to twice MB, let's put this in. Wherever we see MA, this is what we put in. 2 MB UA is equal to 2 MB VA plus MB VB. Can we eliminate something here? Class, can we eliminate something? Trafina, can we eliminate what exactly? What can we eliminate?
Please, you can eliminate an MB.
Good. So when you divide through by MB, you cancel out MB. So we have 2 UA is equal to 2 VA plus VB. And this is your equation 1. Once kinetic energy is conserved, half MA UA squared plus half MB UB squared is equal to half MA VA squared at half MB VB squared. This will go to 0 because UB is 0, stationary. When I multiply 2 by 2, I eliminate half. MA UA squared is equal to MA VA squared plus MB VB squared. I'm told mass of A is twice mass of B. So I substitute that as well. So I have 2 MB UA squared is equal to 2 MB VA squared plus MB VB squared. I can also eliminate MB. So I have 2 UA squared is equal to 2 VA squared plus VB squared, equation 2. Now, in ideal situation, you solve these two simultaneously, but I bet you would have it so tough improving what we were asked to do if you try to solve this two simultaneously. And so the only way out for you to go is to use the coefficient of restitution approach or formula. Please, are you there? Are you there?
Yes, please.
So you can only solve this using coefficient of restitution. And in the coefficient of restitution, we are saying that the relative velocity of approach is equal to the negative relative velocity of separation. Some of you will derive this whole formula. I did that with you. So, okay, but it is from this concept that relative velocity of approach is equal to the negative relative velocity of approaching. So, of separation. So, UA minus UB is equal to negative of VA minus VB. Mathematically, this is what I mean by what I've stated in words. Okay? Because UB